So I think those little calculus phobe videos, and there's only, I think, 5 or 6 of them, and then there aren't any more. But so here, we're going to spend today, we might get close to finishing, and definitely finish tomorrow. So the objective is students will be able to justify conclusions about continuity at a point using the definition, determine intervals over which a function is continuous, determine values of x, or solve for parameters that make discontinuous functions continuous if possible. So continuity implies no interruptions in the graph. You might say that a function is continuous on an open interval if its graph can be drawn with a pencil without lifting the pencil from paper. Discontinuities fall into 2 categories. They are removable and non-removable. Informally, we say that f has a removable discontinuity if there is a hole in the function. So you're going to see your pre-calculus coming in, and that how well that foundation is how simple understanding this concept will be. But f has a non-removable discontinuity if there is a jump or a vertical asymptote. So let's kind of do a little bit of highlighting here. So removable discontinuities are holes. It's like if you plug the hole in, then you have made it continuous. If you're unable to plug a hole in to fill it, like an asymptote or a jump, then it's non-removable. So in number 1, it says f of c is undefined. What type of discontinuity would you say number 1 has at c? This is removable, because f of c has a hole at x equals c. So anytime a function has a hole, that is a discontinuity, and you can fine-tune the type of discontinuity, it's removable. All right, 2a and 2b, I want you to identify the type of discontinuity it has. Let me give you a quick head start on me. All right, so 2a, what type is that? Non-removable. And what's happening at c? Good job. It's a jump discontinuity. What's happening at 2b? There's an asymptote, so we have a vertical asymptote, so that makes it non-removable. And in both of these, do you notice that the limit as x approaches c of f of x does not exist? But in number 1, the limit as x approaches c of f of x, it exists. It's whatever value that is. All right, try the third one. All right, so what do we think about the third one? What type of discontinuity is it? It's removable because it's a hole, right? But in this one, the limit exists. However, f of c does not equal the limit. All right, so the big idea here is this column to the right. On the AP exam, when you are asked to justify continuity, there are 3 conditions that have to be written down, okay? And we're going to put them here, and we're going to practice it a few times in the notes. So there are 3 criteria for continuity. In order for a function f of x to be continuous at a point x equals c, the following 3 conditions must be met. Number 1, f of c is defined. Number 2, the limit as x approaches c of f of x must exist. Now, a caveat to this is that you have to show the left and right hand limits. You have to show those 2, conclude, number 2, that the limit exists. And then the third piece is that the limit value equals the function value. So what we've seen up to this point was that the limit could exist even when there was a hole in the graph. The function value didn't have to exist, and that's fine for just a limit. But now, if I want to say that my function is continuous, that I can draw it with a pencil without lifting it, that means the limit has to equal the function value, okay? So here we're just going to restate this in a nice chart. Types of discontinuities. The graphical characteristics of removable are filling in a hole leads to the continuity in case 1 and 3 above. Algebraic characteristics. If you can factor the numerator and denominator, the denominator will cancel, and that's where your hole is, and that's where pre-calculus comes in. For non-removable, the graphical characteristics are the act of filling in the hole does not lead to continuity, case 2A and B. Algebraically, when you factor, the denominator doesn't cancel and you still have a problem. All right, so we're going to look at an actual part of a free response question. This is 2011. It says no calculator. It says let f be a function defined by f of x equals 1 minus 2 sine x for x less than or equal to 0 and e to the negative 4x. It says show that f is continuous at x equals 0. All right, so the first thing you have to do, and we're going to practice this, there are 3 conditions that must be met. We need to show what f of 0 is. So let's go, which row would I plug into for f of 0? Do I plug in the top or the bottom? Top. So we're going to write 1 minus 2 sine 0. So f of 0 exists, and it's defined. Number 2, I have to show that the limit exists. And I want you to, there's always a method to my madness. In that stand up and talk, I asked you, when is a limit defined? And we said you have to show the left-hand limit and the right-hand limit both exist and come to the same value. So in order to get this part, you're going to do the limit as x approaches 0 from the left. So that's going to be 1 minus 2 sine x. We're going to do the limit as x approaches 0 from the right. In pre-calculus or another math class, have you done the 3 triangular dots that stands for therefore? If not, let's write it here. In upper level mathematics, in honors pre-calc you have, right? Anybody honors? Do you remember using this? Yeah, okay. I'm like, this is common in proof by mathematical induction. So the 3 triangle dots stands for therefore. So therefore, the limit as x approaches 0 of f of x is 1. Step 3, f of 0 equals the limit as x approaches 0 of f of x equals 1. So f of x is continuous at x equals 0. So every single time you are asked to show f is continuous, you need very, very clearly these three things. Okay? Once everybody has made up the quiz, we can talk about, we did overall, I think the average on the quiz was 28 out of 30, so it was really fantastic. I was super impressed. We just need to tweak some notations. Yeah?
Could you use the 3 dots on the AP test?
Yes, and they know what that is. Yeah, great question. You can use the triangular, that's a universal mathematical notation. All right, here's a quick activity. Use the word bank, put the type of discontinuity, and what I want you to recognize is one of them has 2 graphical descriptions, and the other type of discontinuity only has 1 graphical description. So go ahead and fill that in. All right, turn to your table mate and see if you got the same words. And if you're by yourself, turn around, go beside you. All right, so the 2 types are non-removable and removable. So what is one graphical description of non-removable from the word bank? Jump. I think we should start doing that song. Jump. It just popped in my head. All right, what's the other word? Asymptote. Things that pop in my head, and then I'm just going to share you my weird thoughts. All right, how about removable?
Your screenshot stopped sharing.
Oops. I wonder why. Thank you for letting me know. 3034. Yay, there it is. Okay, that was super weird. All right, removable. What'd you say? Whole. Okay, cool. All right, now let's look at this example 1. It says the graph above is f of x. Determine all x values where f of x is not continuous. So we're not talking about the endpoints. So I'm not talking that x is -3 or x is 7. Okay, that's the end of the graph. So we're not going to say there's a discontinuity there. But I want you to list all the x values everywhere else within that parenthesis and classify it as removable or non-removable. All right, turn to your neighbor. Let's see what you came up with together. All right, Maddie, what did you put in your removable discontinuity?
X equals 3 and X equals 5.
Good job. X equals 3, X equals 5. Can you give me thumbs up? Did we get that? All right, Leah, what did you put for your non-removable discontinuities?
X equals -1 and X equals 1.
Good job. Okay, so at X equals -1, we have a jump. And at X equals 1, we have a vertical asymptote. All right, questions on that? Not too bad. So the big idea is removable are wholes. Jumps and vertical asymptotes are non-removable. All right, so in example 2, we're going to do a little bit of pre-calculus here. If f of x equals x squared minus 1 over x minus 1, it says find the x value of the whole. Is there anyone who remembers pre-calc? How do you determine it, Ankit?
When the denominator cancels.
Good job. So you're going to factor your numerator, factor your denominator, and the factor that cancels. So you set x minus 1 equals 0, so x is 1. And then, Sophie, how do we find the y-coordinate of the whole?
You plug in the x value into the equation.
Okay, if I plug it into the original, don't I have a problem?
Yeah, you have to plug it into the factor.
Yes, I'm going to plug it into my factored reduced one. So the whole would be at 1, 2. What would be the graph of f of x? Generally speaking, what would it look like? It's a straight line, right? It's y equals x plus 1 with a whole. All right, example 3. If the function f is continuous for all real numbers, and f of x equals x squared plus 6x plus 8 over x plus 4, when x doesn't equal -4, then they would have to have a separate designation. If I want it to be continuous, so right now I know there's a problem because I'd be dividing by -4, but I could make this a piecewise function. And then I'm trying to figure out what would f of -4 have to equal so it's going to plug in the whole. So what would I need to do to figure this out? Factor it. So let's start there. So that's x plus 4, x plus 2. And you do know that, okay, if we're talking about discontinuities and you have x plus 4 in the denominator, that's your clue that there's an x plus 4 in the numerator. Like if you are not so swift at factoring, like use your clues. Like there's little clues out there for you. So I'm going to cancel here and get x plus 2. So what would f of -4 have to equal that would plug in my whole? -2. Good job. Does that make sense? This is so, like, technically then you would do something like this. You would say a piecewise function, x squared plus 6x plus 8 for all x's not equal to -4, and then it's -2 when x is -4. It would look like that. That's what we're kind of talking about. All right, example 4. Let f be the function defined by f of x. This is very, very similar to this. F of x equals x squared minus 3x minus 18 over x minus 6 when x doesn't equal 6. And it's equal to a when x equals 6. So find a. So let me pause and give you a head start. So this is very, very similar. But do you notice I just reworded the problem, but it really is asking the same thing. My husband went to a business conference, and he just got back last night, and he brought this, and I'm like, if there's anybody who, like, you got some stress, I'm going to leave this here. Anybody want to come in, you want to play with this? It's supposed to be holding business cards, but I told him, I said, I'm going to take this to school. Somebody might need to work something out. I was thinking it looks cute. It looks super cute. All right, so here we go. I'm going to start this one. So this is x minus 6, x plus 3. So then, anybody have it? What is a? Say it again. Isn't it 9? Yeah, you're going to plug in that x is 6. And that's going to plug in the hole. So A would be 9. All right, questions on that one. So you reduce it, and then you have to plug in that x is 6, and that's going to fill in the hole that we have. All right, example 5. Consider the piecewise function defined for h of x below. Determine all x values where h of x is discontinuous and classify each as removable or non-removable. So the big idea here is where the pieces are transitioning at -1 and 2, I need to check left-hand and right-hand sides to see if those limits are the same. So let's look at the limit as x approaches -1 from the left. And a note that I noticed on the quiz, we do need to be careful with order of operations. A negative, if it's x squared, that negative becomes positive. So I'm getting 4. All right, so at x equals -1, h of x is discontinuous. And what type is it? I thought I had my phone on. What's happening there? Is it a hole? It's jump, which is non-removable. How do you know whether it's a hole or not a hole? What has to happen for it to be a hole? Okay, it'll approach the same from the left and the right, but it also factors. You would have a factor cancel and a fraction, okay? So those are things to look at. Now let's try this with 2. So I've got that my limit exists, but what's f of 2? You also, in order for it to be continuous, we've got to check that. F of 2 is 4. So, oh, sorry, that's a little typo. That should be f of x, right? I'm like, why do I have an f over there and an h there? That's just a little typo. So h of x is continuous. Sorry about that. I'm like, there we go. It really didn't ask me to prove that it was continuous, but I thought for funsies, that would be good to write the 3 steps out again. All right, finding domain. This is just a little bit of pre-calculus practice I'm trying to build up your foundation. Look at these 3 scenarios and write down your domain. So stop and think about those functions, because this is going to help us pay off in this course. So state the 3 domains if you remember. All right, in number 1, when you have a fraction, you have to be concerned with the denominator cannot be 0. So I'm going to write these 2 different ways. It does not matter to me which way you write them. You can say x does not equal -1, or in interval notation, that's -infinity to -1 union -1 to infinity. On the AP exam, be comfortable with interval notation, because that's often how you will see it written. In a square root, what do you have to be concerned with a radical? Say it again. Negatives under the radical. So what we do is we set what's called the radicand. The radicand is what's underneath the radical. So you set it greater than or equal to 0. So I could say it's x greater than or equal to -3/7, or I could put bracket -3/7 to infinity. Inside a logarithm, what do you have to remember about inside the logarithm? You cannot have a negative inside a logarithm, and you also can't have 0. Okay, so this is a good refresher for us. So I'm going to set 2x plus 1 strictly greater than 0. So remember, the answer to a logarithm is the exponent in exponential form. So I can't get, say my base is 2, I can't get 2 to a power to equal a negative number. Okay, because even if my exponent's negative, it just makes it like 1/2 cubed, 1/2 to the 5th. I can't make it negative. I also can't make it 0. 2 to the 0 is what? 1. I can't get 2 to a power to give me 0. That's kind of my problem. So I would subtract 1, divide by 2. So I could write it like that, or in interval notation, parenthesis, -1/2, comma, infinity. All right, I'm going to pause a moment and give you a head start. And I made these a little bit tricky. So try example 6. 1, 2, 3. I took it up a notch. Okay, took it up a notch. Let's see if we can handle it. You can't handle the truth. Maybe not, Ruby. These are my random things that pop in my head. Tom Cruise, Jack Nicholson. Anybody? I'm older, so. Now remember, you are doing the domain of the original function. So even though you can do some canceling, I still, like in number 1, I cannot plug in x is 0, right? Even though I can reduce it, I'm still talking about the first one. So the first one's not bad. Domain, you could say x does not equal 0. So that one's no biggie. Ooh, but 2 and 3 get super interesting. All right, turn to your neighbor. Compare answers, discuss, debate. All right, who's feeling confident that would like to tell us about problem 2? Who's feeling like, yes, I can do it? Clara, what do you think? What'd you get?
You said like a bracket and then -5, comma 0, and then the U, and then parentheses 0, comma.
You got it. Okay, so the first thing I noticed, and it's okay to do this, where I'm going to say x can't be 0, but then underneath the radical, x had to be greater than or equal to -5, but it can't be 0. So nice job on that one. Ooh, okay, how about number 3? All right, George, what do you think?
Like a bracket 0, comma 4 with parentheses, union, both parentheses 4, comma infinity.
Nice job. Okay, so the one thing you should notice, I wouldn't say that x can't be 0, right? Because I can plug in 0, but what's going to cause that denominator to be 0? The 4, right? Because, and stop and think about that, 2 minus the square root 4, that's 2 minus 2. But then I also have that x has to be greater than or equal to 0. All right, this is a natural stopping point.